Hi, welcome back to AP Physics 1, Unit 1, Kinematics. In the last video, we looked at representing motion, but we looked at it in terms of equations. So in this video, we're going to look at representing motion in terms of the graphs. AP Physics is going more towards this representation. So there's always it's always good to look at the different views. And like I said, in this one, we're going to look at the graphs. Graphing in physics is very important. Because we can describe a lot of motion by using the graphs, and we can go between all the graphs using math, but then we can also go between graphs, equations, the graphs to narratives, and so forth. So in physics, we really look at three types of graphs. We have a position versus time, velocity versus time, acceleration versus time. So something to note is that your time will always be on the x-axis. And then one of these three, position, velocity, or acceleration, will be on the y-axis. The way you think about it is time is your independent variable, and one of those three quantities is your dependent variable. And what happens is on each graph, we can determine different things about the motion. Even though it may be a position versus time graph, we can figure out the velocity. It may be a velocity versus time graph, we can figure out the change in position, which is displacement, or we can figure out the acceleration. And then on an acceleration versus time graph, we can easily find the change in velocity. So how do we do that? The first graph is the most basic one. It's a position versus time graph. In the last video, we talked a little bit about motion maps, and I said that the motion maps can get turned into these position versus time graph if you stretch it through time. And the main thing that we can determine from a position versus time graph is the velocity. Okay. Now remember, there are two types of velocity. We have instantaneous velocity, which is at a particular moment in time, and then we have average velocity, which is for an entire trip. So the way we look at it is instantaneous velocity would be if we drew a tangent line to the function. Now, for two sets of graphs, and you can see in the table or the picture off to the right here, you have stationary objects and uniform motion. The instantaneous velocity will just simply be the slope of those lines. And you'll see for a stationary object, the slope of that line is 0. Now, the average velocity, right, is a secant line. So remember, secant intersects a graph, a function at 2 points. And what happens is it would be like our initial and final times. So we would draw a line that connects those 2 points and then find the slope of those two. And so between those 2 points, and that would just be an average velocity. Now, on a velocity versus time graph, we can do the same thing, but we're looking at accelerations now. Remember, acceleration is changing velocity with respect to time, while changing anything with respect to time is simply finding the slope. But again, right, instantaneous goes to tangent, and average goes to secant. Now, the good thing in AP Physics 1 is that all of our velocity time graphs will be some sort of line. It'll either be a slope of 0 or a non-zero slope. We will not have any other function on a velocity versus time graph besides some sort of line. Now, the easy graph that you're going to see is simply acceleration versus time. We'll get that here in a moment. But the velocity versus time graph is the middle graph. And so what happens is we can go down, right, to acceleration by finding the slope, but we can also go up to the velocity, the position versus time, by finding the area under the curve. And I like to say this is doing calculus, but not doing calculus, right? So what does that mean? You're using calculus ideas, but not using the calculus principle. And so here in AP Physics 1, the area, when we say the area under the curve, is either going to be a triangle, right, which is 1/2 base times height. It's going to be a square or a rectangle. Now, the reason why I say square or rectangle is because it may look like a square, but by the scale, it's actually a rectangle. So please, please, please pay attention to the scale. Like you may have a 1 second to 1 second scale, like 1 tick to 1 second on your x-axis, but on your y-axis, you may have like a 1 tick equals 10 meters. So even though it may look like a square, by the numbers, it is a rectangle. Now, jumping to the acceleration versus time graph, really the only thing that you're going to find off of this is change in velocity, okay? Because what happens is the acceleration, due to this being AP Physics 1, is always going to be constant, which means you're always going to have a horizontal line. It's either going to have a slope, it's either going to have a value of 0 or a non-zero value, right? The slope won't have a non-zero slope, but you'll have a non-zero value. So if we look at this little diagram chart, you'll see the 3 different types of motion that we have. So the first thing is a stationary object. So an object is at rest. So note that your position is constant, which makes this a slope of 0. Right? So the velocity of this object would be 0. And what you see is what happens is I find the slope of that is 0. Right? Now the slope of this line of our velocity time graph is also 0, which puts my acceleration time over there at a equals 0. Now you jump down to the other constant velocity, right? So uniform motion is our constant velocity model. And so what that means is if I take a slope on a line, remember, it is the same thing everywhere. So my instantaneous velocity would equal my average velocity. So if I find the slope of this line, so that would be a number. So note that now I have a non-zero velocity, but the slope of my velocity time graph is going to be 0, which makes my acceleration value equal to 0. Now you jump down to the next side, right? Constant acceleration. That's what really separates Physics 1 to Physics C. So even though our position versus time graph is a parabola, the acceleration is constant. And so here we would find an instantaneous velocity, right? Or if I connect 2 points, I would find an average velocity. Okay, which means over time, right, my velocity does not equal 0. It is a non-zero value, right, which then puts my slope to be a slope line. And now my acceleration is not equal to 0, which means now I have a value, right? I have a non-zero value for my acceleration. And these all tie back into the equations. So the quadratic equation, the displacement equation, well, that's your equation of a position versus time graph. The velocity, v equals v0 plus at, that is your equation for velocity time graph. And then acceleration is just whatever our number is. All right, so let's look at an example here. So this picture is actually from an old AP question, but I wanted to do some of the principles that we just learned. So we're going to find the acceleration at 5 seconds, which makes this an instantaneous acceleration. But again, the good thing, this is a line, so we have to just find the slope of the line. Then in part B, we're going to find the average acceleration for the first 18 seconds. So again, average meaning we're going to start at 0, we're going to go to 18, we're going to find the slope of that line. And then we're going to find how far the object traveled during the first 9 seconds. So we're going to find the area under the curve. Okay, so part A, we're going to find the slope. Oh, sorry, this should be an acceleration, not a v. So it should be acceleration equals delta v over delta t. And again, look, delta y over delta x. That's our math representation. So I'm going to find, right, the slope. I'm going to do the first point and the last point. Just makes it easier because here's 5 seconds. It's on that line. So this is the point 9, -1. This is the point 0.8. And so I'm going to do final mass initial for both of them. So I'm going to do -1 minus 0.8 over 9 minus 0. And so I got my calculator. So it's -1 minus 0.8 divided by 9, because it's 9 minus 0. And I get an instantaneous acceleration at 5 seconds of -0.2 meters per second squared. So again, all we did was find the slope of that line because that is what instantaneous is. Now I'm going to find the average of the first 18 seconds. So basically I'm going to make a line from 0 seconds to 18 seconds and find the slope of this line. So my point is still 0, 0, 0.8. And now I'm going to be over here at 18, 0. And I find the slope of this line. Okay, so it's going to go average acceleration. And it's going to be 0 minus 0.8 divided by 18 minus 0. So 0.8, negative 0.8 divided by 18. And so I'm going to get an average acceleration of negative 0.044 meters per second squared. Again, average meaning secant. So note that I made a line that connected the 2 points, t equals 0 seconds, t equals 18 seconds. Found the slope of that. And now the last part, we're going to find how far the object traveled during the first 9 seconds. So this is a little tricky one. Students will often make this mistake. They'll do the big triangle, right? This triangle. But note that your 0 point is right there in the middle. So it actually like splits into 2 triangles, a positive motion heading towards back to the origin to a negative motion away from the origin. Okay, so I need to find the area of both of those. So I'm going to do 1/2 base times height twice. And it may be helpful if you plug in the negative sign for the height of the second triangle. So I'm going to do 1/2. My base is 4 seconds. My height is 0.8. And I'm going to do 1/2, 5 seconds, and my height of -1. And so I got 0.5 times 4 times 0.8. That's going to be positive 1.6 meters. And then I'm going to have 0.5 times 5 times -1. And that's going to be negative 2.5. Now it's 2 triangles, so I add them together. And I find that during this time interval, it has a displacement of negative 0.9 meters. Okay, so again, on the top, if we're on the top side, it travels in the positive direction. If we're on the bottom side, it travels in the negative direction. Okay, so as you see, the triangle on the bottom is slightly bigger than the triangle on top. All right, so that ends our representing motion. Next thing we're going to do is we're going to talk about frames of reference and relative velocity. Not necessarily a new topic, but something that's important because, if you change frames of reference, you're going to change motion.